Hello everyone, this is Vibhu Goel from Department of Electronics and Communication Engineering, Government Engineering College, Bharatpur. In continuation of the lecture series that we started yesterday, today we are going to understand the concept of superconductivity. Now, what is superconductivity, what are its classification, and what is the whole physics behind this concept, we'll understand it in detail today. What is superconductivity? We all know that resistance is directly proportional to the temperature. I'm writing it for your convenience. Resistance is directly proportional to the temperature. So as temperature increases, resistance increases, or vice versa. Vice versa in the sense like if we decrease the temperature, resistance also decreases. Now superconductivity is a particular modification of this concept only. When we start decreasing the temperature, resistance also decreases, and a stage will reach when at a particular temperature T, which is known as a critical temperature, this resistance drops to zero. And when this resistance drops to zero, this phenomena is known as superconductivity. But it is that a particular material does not resist any kind of resistance to the flow of electrons, to the flow of current. This is known as superconductivity. So we'll understand it. It's a phenomena in which electrical resistance or resistivity, why? Because R is equal to rho L upon A. Whatever the conductor, whatever the material we are taking, its length and area of cross section are constant. So rho is basically, this is the property of that material. So that's why it's a phenomena in which electrical resistance or resistivity suddenly drops to zero at its transition temperature Tc. As I explained that when we are decreasing the temperature at a particular temperature which is known as a critical temperature, that critical temperature is Tc, at which the resistance drops to zero. So this is a transition from normal state to the superconducting stage, or transition from a normal conductor to a superconductor. So it's a phenomena in which electrical resistivity drops to zero at a particular temperature which is known as a transition temperature Tc, or critical temperature. This concept was first discovered in 1911 by Kamerlingh and Onnes. He's a Dutch scientist, and he observed this particular pattern in mercury. What he observed, this we can understand with the help of a graphical representation here, where we have draw the graph between resistance as temperature and Kelvin. What he observed in mercury, that as we are decreasing the temperature, here it is in Kelvin 4.4, and there's some resistance it is denoting. Now as we are decreasing the temperature at a particular temperature of 4.2 Kelvin, the resistivity of the resistance of this material suddenly drops to zero. Now there are two terms. The first one is the abrupt decrease, and the second one is the gradual decrease. Here we are observing a abrupt behavior. So that's why I mentioned the term suddenly drops to zero. So sudden drop is basically, this is abrupt behavior, not the gradual one. This you can notice. Okay. Now what this graph shows? This graph shows near zero electrical resistance. At this particular 4.2 degree Kelvin, the resistance is approximately zero at about 4.2 Kelvin for the mercury as discovered by Kamerlingh and Onnes. Now what is the uniqueness of this? If you go through a periodic table in which all the elements are arranged in a row and periods, so what we observed, that this uniqueness of superconductivity compared to all other physical phenomena is that it is not related to periodic table in any sense. Like we cannot observe any pattern that if we are going through increasing atomic number, or we are going through a decreasing periodic number, or we are going through increasing atomic weight or decreasing atomic weight, increasing electronic negativity, whatever we are following, we cannot find any particularity in the periodic table. Like if we are going through increasing atomic weight, we will find all the elements having superconducting behavior. No, we cannot find such kind of behavior. Now what is the overall theoretical concept behind it, why it is so? It was proposed by three scientists. These were Bardeen, Cooper and Schrieffer. The theory of it was explained in 1957 by Bardeen, Cooper and Schrieffer, popularly known as BCS theory. This is basically based on the concept of quantum mechanical phenomena. But the scientist proposes that quantum phenomena of the superconductivity. Now what is this quantum phenomena? It is characterized by the Meissner effect. Now we'll understand what is Meissner effect. What is Meissner effect? Simply what you have to imagine is that wherever superconductor is there, it is an enemy of basically magnetic field. Whenever superconductor is there, it does not allow magnetic field to pass through it. This is the simple concept of Meissner effect. So what we took two materials. The first one is a superconductor. First one is a simple semiconductor, and the second one is a superconductor. What we observed, what Meissner effect says, it says that the expulsion of the magnetic field from a superconductor during its transition to the superconducting stage when it is cooled below the superconductor. When it is cooled below the, I think it is wrong here. When it is cooled below the, superconducting is when it is cooled below the transition temperature Tc. So what it is, when the temperature is greater than the critical temperature Tc, as we have observed here. When it is greater than the critical temperature, it does not follow the, when it is greater than critical temperature, it does not follow any behavior of superconductor. But when it is less than critical temperature, it is following the behavior of superconductor. So what Meissner effect says, when the temperature is greater than critical temperature, the magnetic flux density, magnetic field lines pass easily through the conductor. But when it is less than critical temperature, it means the material behaves as a superconductor and it does not allow the magnetic field lines to pass through it. Now, this is the perfect state of diamagnetism. So what Meissner effect says? Meissner effect says that it is the expulsion of basically magnetic field lines from the superconducting when it is transiting from the normal state to the superconducting stage. So this is Meissner effect. Now, to understand what is diamagnetism, I will come to it before discussing about the concept of what is the classification of superconductors at all. First, we will discuss what is diamagnetism. Diamagnetism, hope you people remember when we understand all the electromagnetic induction and Faraday's laws in the subject of EMFT as well as in class plus 2 physics, where B is equal to mu of H plus M. Okay, so where B is nothing but a magnetic flux density, H is the magnetic lines of force, magnetic field strength we used to say, and M is the magnetization. Now, for a superconductor, as we understand in the in the Meissner concept, that B inside the superconductor is 0. Now, if in this particular relation, if we put B is equal to 0, then what we will understand, like below critical temperature Tc in the case 2, when it is B is 0. Now, if B is 0, that equation becomes this. Now, from here, H is equal to minus M, means magnetic field strength is equal to the negative of magnetization. Now we understand one concept of susceptibility. What was susceptibility? This is known as chi. This is known as chi. Okay, this chi is basically M upon H. This is the chi is basically the ratio of magnetization to the magnetic field strength. Now for a diamagnetic substance, diamagnetic substances which does not allow any kind of magnetic field lines to pass through it. So here for diamagnetism, what we understand here now, H is equal to minus F. Now if we utilize this relation here, we'll get susceptibility is equal to minus 1. Now what is the overall conclusion we got? That for a diamagnetic substance, the overall susceptibility is negative. So what it says, it holds true for all the perfect diamagnetic materials. So if I can generalize or conclude the superconductivity, what is superconductivity? Like here is the temperature some T. Now we are understanding the overall graphical relation in between resistivity with respect to temperature. Now when the conductor is normal, it behaves like how it is behaving, because we know that R is directly proportional to T. Now as we are decreasing the temperature, now R is equal to rho L upon A. So R is basically directly proportional to rho. So can you see that rho is directly proportional to T? So when we are decreasing the temperature, there is a decrease in the resistivity. Now when there is a decrease in the resistivity, what we are observing, when it is in the normal state, there is a decrease in the resistivity. Now when this particular temperature T comes to a particular, when this temperature T drops down to a particular temperature, critical temperature Tc, there is a sudden change in the behavior. What is that behavior? That resistivity suddenly falls to 0. Now this is known as superconducting stage. So this was the same concept what Kamerlingh and Ohms understand in the behavior in case of mercury, but it is not like this one. It is if you observed here, there is a gradual. Now this is this you can say this behavior is gradual and this behavior is abrupt in nature. So that's why we use the term sudden decrease to the 0. So this is how resistivity decreases with the decrease in temperature, and at a particular temperature Tc, which is known as critical temperature or transition temperature, it suddenly falls to 0. So this is the overall conclusion of superconductivity. Now we'll come to the classification of superconductors. What is classification of superconductors? There are two types of superconductors, type 1 and type 2. But type 1 says they are basically also known as soft superconductors, and type 2 are generally known as the hard superconductors. But the soft superconductor typical examples are like mercury, lead, and for type 2 superconductor typical example is yttrium, barium, copper oxide. Okay. What is type 1 superconductor? So type 1 superconductor is that their superconductivity abruptly destroyed when the strength of the field rises above a critical field. So what it says, this is like when the field rises above the critical field, their superconducting behavior suddenly drops. So after critical field, the behavior is normal behavior. So these are soft superconductors, these are type 2 hard superconductors. These are relation between M and H, and mind, it is minus M, it is not M, it is M and H. So this graph is basically indirectly giving the overall susceptibility behavior. But susceptibility behavior is like with the increase in H, M is increasing, with the increase in H, M is increasing, they are in proportional to each other. So every time the ratio is 1 with a negative sign, which indicate the susceptibility is negative, and which further indicates that it is following the perfect diamagnetism stage. So what it says, like after a particular critical field, the overall behavior becomes 0. Now, how about type 2 superconductors? These are basically hard superconductors. They follow a particular mixed state, which is known as vortex state. What it says, in type 2 superconductors, raising the applied field past a critical field value HC1. Now this is HC1. If we are increasing the field, if we are increasing the electric field, so what it says, raising the applied field past a critical value, it leads to a mixed state, which is known as vortex state. Now this is vortex state, mixed state, in which increasing amount of magnetic field penetrates the material, and at second critical stage, superconductivity destroyed. So after this, there is no more superconductivity behavior. So this is the normal state. So this is all about your type 1, type 2. So what is superconductivity, how Kamerlinger norms observed it in mercury, and what is the overall uniqueness in the concept of the perspective of periodic table, what is the overall theory behind it, then what is Meissner effect, and then how about this Meissner effect leads to a state of perfect diamagnetism, then what is diamagnetism, then we understand how through diamagnetism susceptibility is negative, then we conclude the overall behavior of a superconductor with the help of R and rho, where it is gradual and then abrupt change at a particular critical temperature. And then we understand overall the classification of superconductors type 1 and type 2. The one is soft one and the second one is hard one, and how after a particular critical magnetic field, it comes to a normal state, whereas it comes to a mixed state, which is known as vortex state. So this is all about superconductivity and their classification and Meissner effect. So just go through it. If you have any doubt, drop a message, and stay safe, stay healthy, stay at your home, and follow the proper hygiene. Tomorrow we'll continue with the London equation of superconductors. Thank you.